Hi, this is Professor Fernandez. We are working on class note C in lesson 12. So in this class notes, I want to piece together the theorems that we've been talking about in this lesson to finally help us figure out when a linear system AX equals B has a unique, infinitely many, or no solutions. Right? So as a quick little recap, we know the answers to each of these questions, but we haven't put them together yet. We have results for them. For example, we have Cramer's rule that tells us that the linear system AX equals B has a unique solution if and only if the determinant is non-zero. And then we also have answers about when the system AX equals B has a solution, to begin with. That's when B is in the column space of A. That was the first theorem we talked about in this lesson. And certainly it has no solution if B is not in the column space of A. And then in this theorem right above that I'm going to scroll here, we have information about whether or not the system has a unique solution or one of these other two categories based on the linear independence or dependence of the columns. So we have lots of results that we can draw on to answer this question now. So this is the point of this example, to show you how you would put together these different theorems to answer questions like this. So let's see what the question says. Consider the system AX equals B, first with this matrix A. Determine whether the system has a unique, infinitely many, or no solutions for each of these B vectors below. So I'm going to start with this first B vector, right? And how would I answer this? So in general, the first thing, I'm going to look at two things when I am answering questions like this. The first thing I'm going to look at is the determinant of the matrix, if I can do that quickly. All right, so let's look at the determinant of this matrix, and I'll explain why I'm doing that in a minute. The determinant of this matrix, if I expand about the first column, then it's just 1 times, getting rid of this row and this column, and I'm left with that matrix, 1 times the determinant of this matrix. So I'm doing a cofactors and minors expansion back from a previous lesson. And the determinant here is 0, right? So what I learned is that the determinant of the matrix A is 0. So I know from Cramer's rule from a little while ago in the course that AX equals B is not going to have a unique solution, right? Cramer's rule requires non-zero determinants. So I already know that I'm in the case solution category of either infinitely many or no solutions. How do I differentiate between infinitely many or no solutions? Well, this one has a bunch of solutions. This case has no solutions. And as we talked about in this lesson, the condition for AX equals B having even one solution is that B is in the column space of the matrix. Right? So I know that I am in these two cases, one of these two cases. I don't know which one, but now I'm going to use the column space to distinguish the two. So I'm going to say, oh, okay, remember that AX equals B has a solution if and only if B is in the column space of A. So this is like the second thing, my go-to question. First one is a determinant, second one is this. So what is the column space for this matrix? This is the same matrix that we worked with in previous video in this lesson, and we wrote out the column space. It was the set of linear combinations of the columns. So I'm going to write that here, 1, 0, 0 plus x2, 2, 1, 0, and then x3, 4, 2, 0. So I want to know if this B, the first one that I'm looking at up here, if this B is in the column space. The question is, can I find quantities x1, x2, x3 that make this equation true? And you can see that the answer is no, because the third component in the left-hand side, if I were to write this as a vector, the third component is 0. And I am trying to figure out if this can ever be equal to the vector 1, 0, 1, and the answer is no, right? 1 and 0 are not the same number. So this can't work out. So I now have concluded that there are not even one, there aren't infinitely many solutions, there isn't even one. In other words, there are no solutions, okay? So I'm going to remove all this clutter here and just write out the result. So the question was, Determine whether infinite many. So for this one, no solutions. Okay. I still know that the matrix A has determinant 0. So I still know that regardless of what the B vector is, I am in either this case or that case. And again, which case I'm in, we can determine based off of the column space and other information. All right. So, all right. Let me erase here so we can consider this second case. So, what if B is equal to 1, 1, 0, which is up here? Right. So now I can redo my analysis, right? Question, is this in the column space of A? Well, the column space was x1, 1, 0, 0, plus x2 times 2, 1, 0, plus x3 times 4, 2, 0, right? Can this be equal to 1, 1, 0? Well, in this case, the third component is 0, so that's great. And then I'm left with two equations. If I write out the first row on the left-hand side, this is very similar, it's exactly the same actually as what we did in this previous video in this lesson. If I write out the second row, that's x2 plus 2x3 equals 1. You can see on the left-hand side that I have 3 variables that I can play with, but I only have 2 equations. So that's going to give me an infinite number of solutions. And I'll just walk through very quickly how you could see that explicitly, right? So if I write this system out in augmented matrix form, and I row reduce, I say I'm going to replace, this is 0 here, I'm going to replace the first row with the first row minus 2 times the second row. That means that I'm not going to change the second row. There it is. And I do 1 minus 2 times 0, that's 1. 2 minus 2 times 1, that's 0. 4 minus 2 times 2, that's 0. And then 1 minus 2 times 1, that's negative 1. You can see from here that I get x equals negative 1. And then this is just like basic, x1. This is just x2 plus 2x3 equals 1. The set of points that satisfy this equation is a line, right? There are an infinite number of points that satisfy this equation. So I do get an infinite number of solutions, so that's the particular case that I have narrowed it down to. I don't get no solutions or an infinite number of solutions. So I'm going to say here infinitely many solutions. Okay, so that illustrates a little bit again of how we would put together these different theorems. I didn't use the theorem that I used above, the theorem that's listed right above this example. I just used information about the column space and information about the determinant. So that's kind of the point of this next example, to show you how to use a different mix of these theorems. So let's consider what this example says. Consider the system Cx equals B. So now I'm looking at a different matrix. Same questions. If I have these two B vectors, do I have a unique, infinitely many, or no solutions? All right, so this is a different matrix C, so I'm going to start in exactly the same way. I'm going to try to calculate its determinant. And just looking at it here, right, going back to thinking about cofactors and minors, I want to find a row or a column that has lots of zeros. So once again, this column has lots of zeros. So I'm going to use that column to expand the determinant. So it's going to be 1 times the matrix determinant of the matrix obtained by removing the first column and the first row. And then I look at this determinant and I just get 1 times 1 minus 0. So I get 1 times 1, so 1. So this matrix C has determinant 1. So that is non-zero. So I know that from Cramer's rule, thinking about B here, since determinant of C is not equal to 0, Cx equals B has a unique solution. Okay, great. So how am I, gonna figure this out for this particular B here? Well, so I know that Cx equals B has a unique solution from Cramer's rule. I don't have any restrictions from Cramer's rule on B being in the column space of A. I don't need to know that. Cramer's rule preceded that lesson, this lesson where we talked about the column space. So actually, I know that for both of these B vectors, I am going to have a unique solution. So in this case, this is one of the reasons why I like to check the determinant first. So that pretty much tells me I'm done. So unique and unique. Okay, but let me scroll up and show you again how you might have pieced this together from this other theorem. So if I were going back to this theorem, I would say, oh, okay, so has a unique solution if and only if the set of columns of A is linearly independent. Again, notice that, just like Cramer's rule, this is not requiring that B is in the column space. It says nothing about B being in the column space. All you need to do to conclude that AX equals B has a unique solution using this part of the theorem is to check that the columns are linearly independent. So because the Cramer's rule is my first gut instinct when solving linear systems, I checked the determinant. But suppose I had done something differently, and I either don't remember how to check the determinant, don't remember Cramer's rule. Well, if I were using that theorem, then I would just have to see if the columns of A are linearly independent. So I would be doing this check here. So I'm just writing out the columns of A, and I'm going to check if they're linearly independent. Later on in this lesson, we are going to see how Cramer's rule along with this theorem combine to give us actually a new way to check whether vectors are linearly independent or not using determinants. But for now, I'm going to go back to the condition that we have been using, which is checking whether the linear combination when set equal to 0 implies that all of the coefficients are 0. So I'm just combining the vectors here into one vector, and I get C2 minus C3, and then I get just a C3 down here. All right, so if I look at this and I look at each row and pop it out as its own equation, I get C3 equals 0. So that's 0, and then that gives me C2 equals 0. So that's 0, and it kind of, recursively goes up and gives me C1 is 0. So indeed, C1 equals C2 equals C3 equals 0. Therefore, columns of C are Li. So by our theorem up here, right, we know that since they're linearly independent, Cx equals B has a unique solution. So by theorem, oh, I forgot the number. So anyway, I'll skip that. Rather than subject you to additional scrolling, we know Cx equals B has a unique solution. And again, it doesn't matter whether B is in the column space or not. That is not a condition of the theorem. So it works for any B, right? So again, we reach the same conclusion, unique solution. All right, so notice that as designed, the point of this example was to show you how we can distinguish all three cases now of solving linear systems using a combination of all the results we've talked about so far, using Cramer's rule, using this theorem, using column space concepts.